Alright, this is my induction motor generator. Basically what I have done is I have taken a standard induction AC motor, which is this, which was off of an old air compressor, and I've connected it to a weedwacker motor. Now the only problem I ran into was when I connected it to the weedwacker motor in this fashion, where I put a pulley on the end of the shaft. I had to take off my recoil starter in the shroud, and I used those mounting points to mount it to this board. So it's basically just belt driven. Then I also lost my fan, because the flywheel is also your fan for cooling the engine. I installed this electric fan here, which will start to cool the engine once the generator starts to generate power. And basically how this thing works is this electric motor will serve two functions. First of all, I will plug this AC cord into the wall, and that will run the motor to start turning the gasoline engine. Once the gasoline engine fires, then the output, which formerly was the input, goes to the capacitors, which you'll see in a minute. Now basically I have some switches here. This stop switch and run switch, when it's in the run position, opens up the path to ground from the coil on the gasoline weedwacker engine. And when this is put to stop, it'll ground that coil, and that'll stop your spark, and the engine will in fact die out. This switch here, start, which I'm not going to hit it because I already plugged it in, will send 120 volts into this wire, which will go down to the motor. So this will act as a regular motor, as if you would just plug it into the wall. Then, once it's started, you put it in this mid position, which is absolutely nothing. Let the weedwacker engine heat up for a minute. Then when you put it in generate, it will take this wire that goes to the motor, and instead of connecting it to your wall, it'll connect it to a bank of capacitors, which you'll get to see next. And from the bank of capacitors will go into this outlet. Now, there's two things to keep in mind with this. Your capacitance is your voltage. So I have a whole box of miscellaneous scrap capacitors, and I have taken a reading on this with a capacitor checking meter, and I have written the actual value of the capacitor as per the meter. So basically what you would want to do is just keep adding your different capacitors together until you get enough capacitance to give you the appropriate output voltage. I'm going to do that right now. Okay, I'm just finishing up. And I've also put a few turns of electrical tape around it just to hold them in place so they don't fly all over the place. Now I've got three things here. This, should I follow the wire back, goes to the generating light on the panel, which you saw earlier. This just goes in parallel with any of the capacitors, because since they're wired in this fashion, every capacitor it's basically just one giant capacitor. The system only sees the total of all of them. It doesn't see each individual capacitor, so it doesn't matter because they're all in parallel. Next, this is the outlet that you'd be plugging your loads into. This, again, any two terminals, because the power is actually present at the capacitors. So that's where you're pulling it from. And this is a wire that goes from the motor terminals where your AC in would normally go, and it goes to the capacitors, because it's using the capacitors to help charge, keep like a field active in the motor, which will allow this to keep charging. The fan must stay plugged in at all times to provide cooling to the engine. Here is my splitter. I'm going to plug this, which is going to go to my voltmeter, into the one plug and split it off so we can monitor our voltage and our frequency. And we're just going to plug this into our meter. I'm going to turn the meter on to AC volts. I'm going to grab a fluorescent light is a load to this. Make sure the bulbs are in tight. And we're going to use this to demonstrate a load. As far as our frequency, about 61. Now if I do something that's going to slow the motor down, whoops, I didn't mean to stall it. The faster the motor runs, the higher the frequency is going to be. Now with it in volts, I'm going to dump a load on it by plugging in this fluorescent light fixture. And as it fires, it's not firing. You'll also hear it load the motor down an additional. See the light over there, light. As you can hear, this motor is undersized. I'm running it with a wide open throttle and just the field voltage, charging the capacitors, if you even want to call it field voltage, just charging the capacitors pulls this motor down quite a bit, which doesn't really leave much left to pick up a load. So I have actually was able to obtain another motor. It's a 4.5 horsepower gasoline engine, 4-stroke. I'm going to mount this to this board. I'm going to have to disassemble some of this. And I'm going to try a stronger motor. So real quick before this is gone forever, we're just going to take a close look at how it's designed. Basically the motor, weedwacker engine, and it's just mounted on. I took the shroud off where the recoil starter is. There's your capacitors. And that's basically, it's just a frame that holds that steady. There's your cooling fan. And if I get these capacitors out of the way, you'll be able to see that that's how I did it. I put the pulley on the output shaft. See, there's your flywheel. And it just connects with a belt over to the motor. And there's your pulley. So we're going to try to use a different engine that's more powerful and see if I can't get better results. Because the biggest problem I have now, since your capacitors are your voltage, once I start to add capacitors, I start to go backwards. However, my engine RPM also starts to drop. So am I going backwards because I'm maxing it out, or am I going backwards because this motor is not big enough and I'm losing the RPM? Well, we're about to find out.